Please join me in welcoming the ENSCO Railroad Inspection Team.
There we go. All right, good evening, everyone. My name is Ethan Peterson. I am the team leader for this year's 2019 ENSCO Rail Senior Project. Our team is composed of Dan Gibson over on the left, Jake Ballantyne, Garrett Poole, Luke Blaskowitz, Ben Kerber, and last but not least, Elizabeth Donahoe. So this year, we're presented with this project as one of our many options in September. The way this process works is we went through, named our top three, and then the teams were decided by, I think, Dr. Yu and maybe Ruber. I don't remember exactly who was in charge of that. And they put us all together on a team, and I couldn't be more happy with people I've gotten to work with, and I think they would all say the same. So what our project was Ron Lane, our corporate sponsor from ENSCO Incorporated, came to us and had a problem. Their company runs a series of sensor equipment that tests railroads across North America, so Canada, Mexico, I think even Mexico, United States. And the system we're working on is a geometry measurement system. So you'll hear the word TGMS a lot tonight. That's referring to the track measuring system that we are facilitating, essentially. So in this picture, this big bar that goes right across here houses the TGMS. We call that the TGMS bar for short, essentially. And in that, there are all the sensors. And our problem was, as you can see here, it is in its up position and it goes down when the truck goes on the railroad tracks. Our problem was to make that system go from manual to automatic. So the old system was that the workers or the drivers of the trucks had to get out of the truck when they got on the rails, go to the front of the truck after putting on the wheels, and then lift this roughly 100-pound device up or down based on whether they were going off or on to the railroad tracks. So we wanted to eliminate that. That was the first problem. The second problem is, as you can see here, this is relatively high. It's above the hood, and behind that bar is where the driver sits. So the driver's view was relatively impaired while they're driving on the road, not on the rails. So our second goal was to get that in a stow position, out of the way of the driver, so that they can drive safely and not cause any accidents with the trucks that are already big enough and hard enough to drive. So I think that covers the basics, and I'm going to hand it off to Ben, who's going to start going into the subsystems more.
All right, so once we started to work on designing this project, our advisor, Dr. Yu, advised us to move into a conceptual design phase where we would start to put together some different designs and then decide which would be the best moving out of that. So up here we have our three main designs that we worked with, and these were pioneered by Ethan, Dan, and Luke. So Ethan's design here is design one. That's the pivot arm design. It has two interlocking arms that kind of remind of how a plow might be moved on a truck that would be lifted up. But as you can see there, the TGMS would sit down in front in its measuring position and then rotate up and face forward on top of the C-channel. Our second design was this link arm design. We also nicknamed that one the horse head. As you can see, there's like a weird looking horse head piece there. And that was Luke's design that he worked with. This one was very elegant in the way it moved, as it would stay facing the ground at all times and work from that position all the way out and around and sitting on top. And then the third design that we have here is the scissor arm design. That was the one that Dan worked with. And this one had a piston kind of working scissor lift, similar to how you might see on a lift outside, just inverted, lowering it down and up. And so moving into which design that we chose was actually that scissor arm design, the one that we talked about third. And we did this for a multitude of reasons. The main reason was that it was the simplest and easiest to manufacture. It also really worked well with how Ron kind of saw this project working forward, was some of the things that he really wanted. So it was most repeatable, as in durable, and would sit in the right position. Had the most ability to be manufactured, as I mentioned, and was definitely least likely to impair headlights or vision of driver. So after seeing that this met our PDS requirements, we decided to move forward with this design. We went through a concept selection to kind of decide which would be the best, and we have all of our PDS requirements up here. We decided which ones of those would be the most important, and then we rated each design on those criteria. And as you can see down here, Dan's design, which was that scissor arm, came out on top. So after we decided on this design, we started moving forward into embodiment and really getting this design put together and really worked out. So up here you can see our final render of what it looks like now. If you were able to make it to our poster presentation, this is pretty much exactly what it looks like on our mock-up now. And obviously there was a lot of change from that first design that you saw with Dan's, with that long piston working through the middle to where it is now. In this design, there's a piston in the middle of those two tracks that actually just moves horizontally, that lifts it up and down, similar to a scissor lift. So after we really got our design worked out, that was our first semester's goal, we moved into the second semester, and that is where we started working on manufacturing and actually getting this thing built, getting an example built for Ron to say, this actually works. So how we went about that was by splitting up into subsystems. We have 6 subsystems up here. One of them is actually not really a part of our design, but it is definitely something that kind of really had to go about being done so that we could actually make a system, make a full working product. And that first system is the mock-up. That was basically a makeshift truck that would have a bumper and hold our whole design, but also not take up as much space as a truck and still be able to hold everything that this Chevy Silverado was able to hold. So other subsystems that we split up and kind of divided amongst our team members were the mounting system, which were those arms that hold it, the scissor, which was the scissoring arms and the rollers in the tracks, our sliding mechanism, which was those tracks, stoppers in the tracks, as well as rollers. Positioning was stoppers, as well as the bottom system that would hold it level as it moved up and down, and then finally our hydraulic system, which was how we decided to power this. So to talk about that C-channel mock-up a little bit, this was obviously an interesting problem to go about, as it had to be something that was lightweight and cheap, but still able to hold this very heavy system that we were planning to build. The system ended up being about 450 pounds hanging off the front of that C-channel. So we decided to mock one up in Creo. The inspiration for this design kind of came from an engine hoist. We originally kind of were looking at a tripod situation, and then we spread it out to just be a little bit more stable and to be able to hold it sideways as well. And as I said, we went with wood just to try to keep cost and weight low so that we'd be able to move it around, as it was in 3 different places in Hoyt throughout our project as we were building it. One of the main real big problems that we had to deal with was how to mount that C-channel to the front there. We actually have 3/4 inch wood bolt that have hex heads on the front that mounted that C-channel directly into the wood. That was obviously just an interesting problem of how to make this thing be able to be holding what we needed it to hold. So now we'll be moving into some different subsystems here.
Yeah, so one of the main challenges we had to tackle first semester, and actually a little bit into the second semester as well, was a proper way to mount our system to the frame of a truck. So we don't really have the time or space right now to go over all the different iterations we went through during the first semester of a proper mounting technique. But as you can see from this before picture right here, we thought simply of just taking A500 steel tubing, running it up and over to give us proper distance above the truck and also proper distance out from the truck. Then in turn, welding that to these 2 brackets through the use of angle iron, and then bolting the brackets to the C-channel. Now, in retrospect, looking back at that design and where we sort of were, there's basically 3 fatal flaws with that. The first is the A500 steel tubing is relatively heavy, and also, as you can see, there's no support at all, so this system is heavily cantilevered, which is a recipe for disaster. Secondly, the brackets themselves don't really encompass the C-channel, they just cover a little section of it. And then finally, the 4 bolt holes is the only thing that is holding this system up to that C-channel. So we wanted to really address that, and actually it was funny, when the first semester was winding down and we were presenting this presentation in front of our class, Ethan and Dan said, hey, what if we try these brackets out of sheet metal instead? And that's where this concept came about. And so as you can see, this final concept that was generated in mid-February has a lot more benefits than that design has. First off, the plate not only encompasses the C channel, but it extends further and back, and so do the brackets. This adds for extra depth. The brackets are welded along these edges, and now the system is a lot more stable instead of just cantilevered as soon as the weight pulls down on it. Secondly, we added bolt holes up there so we could bolt into the tracks, but not only that, using sheet metal allows us to weld much easier and eliminate the use of angle iron as a whole. And so finally, Dan will talk about this a little more later, but these play a crucial role in our design, and again, if you saw it in Hoyt, you know why, but they provide a stabling mechanism for our system. But enough with sort of the pretty stuff. Dan and I spent a lot of time on all the parts of the assembly running finite element analysis, or in essence, finding out if we put force on this thing, how much stress will it experience and how much displacement it will undergo. So we don't have all the pictures. Dan actually has a cool thing to show you in a bit, but this is just some FEA analysis of it. So what we did is we took our system in Creo, we put 700 pound force down, and then 300 pound forces in the X and Z directions. So this system is experiencing a strong weight pull to the left. The force down is to simulate the weight of the metal, and the forces in the X and Z are to simulate the force of a truck stopping, or just extra forces where it shifts and it has to catch itself and right itself again. So as you can see in this analysis, the max stress was 28,000, and that was at the back of the C channel. But in turn, running that analysis again and bolting these to the tracks reduces the stress in the back C channel and reduces that stress to around 12,000 PSI, which was very substantial. And so before going on and talking about other systems, we just wanted to personally thank On the Edge. No one from there is here today, but they really worked with us great. In fact, this whole system would cost us over $1,000 to make, and they gave it on the house as a donation to Grove City College. So they have laser cutting capabilities, bending, and they were a great company to work with. So now Luke was up to talk about the slide mechanism.
So the track and trolley system is what comes next in the assembly order. This is composed of 2 tracks, 4 trolleys, a series of stoppers and specialized pins, as well as 4 arms. So first, the first step that we took with this system was running FEA, or finite element analysis, on the tracks. We wanted to make sure that the trolleys could easily roll through the tracks without hurt from stress or wear and tear. From there, we then moved on to the arms. We wanted to solidify what our dimensions were for the arms, because that would determine the positioning of the system. So after we ran FEA a couple times on the arms, we realized that we actually needed to add a little more material around these arms to keep it from failing the stress. Once we got that length hammered out, we then moved on to figuring out where we wanted the TGMS to stop in its measuring position and its stowed position. So ENSCO actually gave us a qualification to follow for a measuring position. We had to keep the TGMS when it was measuring about 6 to 6.5 inches above the railroad track. So that wasn't too hard to achieve. The tricky part was getting it with the stowed position. We had to figure out the ideal angle that these tracks would meet with the arms. And as these arms come closer and closer to 180 degrees, more and more force is put on them. So what we ended up deciding for our angle was 6 degrees. This would give it ample spacing and protection as it was stowed, but it would also keep the TGMS and arms not so stressed and fatigued. Moving on from there, then we had to answer the question: how do we stop the TGMS in the resting and stowed position? So that's where we designed a series of stoppers. So for the measuring position, we have 4 1-inch steel blocks, 2 in each track, and what happens is these trolleys will slide forward and they will hit simultaneously each of the 4 blocks, stopping TGMS about 6 to 6.5 inches above the ground or above the railway. Now moving on to stopping it in stowed position, this was a little more tricky. Instead of stopping the trolleys, we decided we wanted to stop the piston. And this required 2 simultaneous stoppers on the right and the left. And after we ran force calculations and ran FEA a couple of times, we concluded that the best design for this would be to hook the stoppers into the tracks and into the brackets that Garrett had designed. This way the stress would be distributed, and we could be confident that the stopper will be able to hold. Now Dan will talk to you guys about positioning.
The sub-assembly that I worked on this year was the lower mount to the TGMS. So when we got this thing, basically Ron gave us this shell, and that was where ENSCO puts their sensors and stuff in. And our goal is to get to move up and down. So in order to do that, we had to find some way to mount the shell onto the arms. So this is the system that I worked on designing this year. And I put up here a funnel shape because basically that's what the design process was. It was basically a funnel of taking designs, using what worked, and then ditching what didn't work, and just narrowing it down until we got a prototype. Basically, the first step that I went through, the first phase, was based on specifications that ENSCO gave us. So for example, in that phase, I was really concerned about features and geometries. So obviously, these different mounting points had to be the right distance away. Another example of like a feature would be these rubber isolators had to be there. So we couldn't just mount this thing right and weld it right onto the TGMS. We had to have this lifted off so we could put those rubber isolators in, so that when it's testing the rails, then it's isolating the vibrations. Another example of something is what Garrett was talking about earlier, the interface between his parts and this. So you can see here there is a curved metal bracket on the back, and that helps the TGMS to just slide up and down very nicely and in a straight line. Additionally, we have a clamp back there so that when it's in the down position, we can just clamp it in. That all looked really good on paper, and that's where I was at the end of the first semester. But then there was a problem. What I had made, and you can see this is basically what I had there at the end of the first semester. The problem was it wouldn't hold any of the weight that it really needed to hold. In order to solve this, I attacked this whole subassembly with what Garrett was talking about, finite element analysis. We have the parts made on the computer, and then we just run simulations where we apply forces to the parts to see, and then we get results back and see where is it weak, where is it too weak. So knowing that, then I would make some design adjustments and then go back, run it again. Okay, still too weak in this area. Go back, run it again, so forth and so on. Finally, I came to a point where I was convinced that the assembly that I made was going to stand up to the stresses that it needed to in the real world. But again, I had another problem. Couldn't really manufacture it easily. Shops are limited in what they can do, and we didn't have a NASA-sized budget. So basically, I had to figure out a way that we could manufacture this. So for example, some of the sheet metal I had to make thinner so that it could actually be bent in a normal-sized shop. Some of the parts I had to rearrange so that they could actually get in there and weld it together so it wasn't blocked by other things. Finally, again, looking at FEA and then with those final design and manufacturing considerations, I was able to make an assembly that I was convinced would be strong enough and could also be made. And that is what we had today in Hoyt Hall, the prototype. I'm going to show you a quick little video of just, this shows a lot of the pictures of the different iterations that I went through in this design process. And hopefully this just gives you a feel for, it might look simple right when you look at it, but this design has gone through maybe like 30 or so iterations. So there's where I was at the end of the first semester. You can see making minor changes with that horizontal bar. And now, okay, the bar is getting longer. There it gets longer. Now you can see messing with the nubs on the sides, messing with supports along those curved braces there. Different styles for those. Then the middle bar gets thicker. And we settle on a final support system to go across. And that's where it ends up. So. Next, I'm going to hand it off to Elizabeth to talk about the hydraulic systems on our model.
So the last subsystem we need to talk about is the drive mechanism. We looked through many different types of drive mechanisms, but we ended up with the hydraulic cylinder. This is just because we integrated it into ENSCO's system pretty easily. It works in all different weather conditions, and it definitely has enough power. The ENSCO trucks actually already have a hydraulic pump on them that's used to kind of push and pull their rail system down and up. We ended up deciding on using the hydraulic system and integrating a diverter valve to get it in there. So you can see this is kind of a drawing of the hydraulic circuit. Here's the diverter valve, and over here is where the hydraulic pump will be coming off of. So the pressure from the diverter valve will actually, it'll push into our cylinder as well as the front rail gear. Because I'm very conscious of safety, as Ron knows, we integrated a PO check. This is just so if the entire system loses pressure, ours won't fall. It'll stay exactly where it needs to be. Right up there you can see the Maverick 3000. That's the hydraulic cylinder we ended up choosing. It puts out about 3,000 PSI and it has a 20-inch stroke length or extension length. Up here is just a kind of an aerial view of the hydraulic setup we ended up choosing. We worked with a company called RJ Hydraulics, which created some custom hoses for us. And as you can see, it kind of weaves around and it actually goes up the mounting mechanism that we have, goes around and avoids all the trolley systems to go into the hydraulic port. As of right now, we actually have the pump directly hooked up to the hoses. This will change whenever we integrate it into the system because that diverter valve and the PO check will be included. Now I'm just going to hand it off to Jake. He's going to talk a little bit about the economics behind everything.
So looking at this project, we were granted a very generous budget of about $5,000 when we first started out. So looking at that, we kind of have to spread that around a little bit, see who needs what for the system. As you can see, the hydraulic system was the biggest number. A lot of that was just the custom parts that we got, the custom hosing, and the cylinder is not necessarily cheap. As Garrett mentioned, we also did get a really big boost from On the Edge. They really helped us a lot out. With that, give us about $1,000 in free parts in participation with our project, so that was really helpful for us as well. So just looking into some of the analysis of what we were spending, this is a sensitivity chart. It kind of highlights where we spent most of our money and highlights what are some of the more important aspects of our system. So as you can see, the hydraulic system is a little more expensive than the others, but then it's a generally normal distribution. As we go down throughout these systems, as you can see, our truck mock-up and some of our miscellaneous parts were some of our smaller expenses, which is good because we were able to put most of our funding into actually building what our product was, which we were really happy about, and there was not much that we were not able to use. Moving on, looking at the Pareto chart, this is similar to a sensitivity chart, but it looks at how much our system grows as we spend more money. So as you can see, it's a large spike at the beginning, but it is a relatively normal curve as we continue spending. There aren't one or two systems that spend $4,500 or a $5,000 budget, and then we only have a little bit left for everything else. We were able to spread our finances around pretty well, which we were happy about, and we got everyone exactly what they needed. This number here is about $4,500. This is our estimate, our general estimate for what it would cost if this were to be recreated. So this is a little higher than it normally would be. We got it down to about $4,000. We do want to thank On the Edge again. They helped us out towards the end, making some brackets that we did need in a time crunch. So that was really helpful for us as well. But this is what we estimate it would cost. As you can see, it doesn't include the miscellaneous or the mock-up because we didn't necessarily need all of those things. So this was only including what would be necessary for the system, included in with the On the Edge parts that they did give us for free. This is included in that number as well. So that's just looking at our financial overview. And now Elizabeth will be talking a little bit about our PDS completion.
Just to review our PDS, we wanted to create a product that could raise and lower the TGMS system automatically, which we were able to complete. We also wanted to create a product that would not impede the driver anymore, would not impede the headlights or the blinkers. This was done by keeping that TGMS system really close to the front bumper, and we were able to attach that on that CD channel as we talked about. The last part of the PDS we kind of changed a little bit. Originally we were going to have the actuation system on the inside of the cab as well as on the bumper. We ended up changing that because we talked to Ron and we ended up figuring out the drivers actually need to get out of the cab no matter what, so it made it a little bit easier. We were able just to secure the actuation just on the bumper. Overall, just over the past year, we have been able to work in a continuously evolving project where we've really learned what it means to be mechanical engineers. We not only had to start from scratch with this project, but we actually had to come up with designs, pick the best one, and then perfect it to the best of our abilities. We not only did CAD drawings, as you guys saw, but we had to work in it with FEA, work in the shop. We had to work with electrical and hydraulic equipment, as well as talk to these outside companies like On the Edge. And this has been just an amazing learning experience for all of us. By going through this whole process, we have been able to kind of solidify all the information that we've learned over the last 4 years, as well as getting some great public speaking experience, as you guys are seeing. And we just wanted to thank everybody so much for all their work that they put into us. And also we wanted to show off a great video because we did come up with a working product. So here's our lovely video.
Wow.
Pay no mind to the people in the background of this video who are not dressed. Just to finalize, I just wanted to thank everybody so much. Thank you, Dr. Yu, our advisor. Thank you, Ron Lang. We really appreciate all of your work. Thank you to Jim and Kara and all the shop assistants and Stephanie Adams. And we also wanted to thank the 2 companies On the Edge and RJ Hydraulics we worked with. And of course, we just wanted to thank all of you for all your time tonight. It's been absolutely amazing this semester, and we appreciate you coming and listening to this very long presentation for us. Thank you so much, guys.
Just a comment, we have Ron Lang with us tonight. Ron, just put your hand up so they can see this from ENSCO. Ron is an alum of our program, and 22 years ago, I guess he was right here, okay, doing this thing, not in this building, but, Dr. Klaus and myself had him as a student, so we're really happy to have him back, and it makes us feel like 100 years old. So. Okay, we have time for a few questions. Yes?
The hydraulic cylinder you chose, what advantages did it have over other cylinders you considered?
I could.
Can
you
you repeat the question and then?
So the question was, what were the advantages of using the hydraulic cylinder we chose? One of the criteria that we had to work with was the onboard pump system that the truck had already integrated. So that truck runs a certain PSI range of pressures, and we had to fit our hydraulic cylinder into that range of pressures. So like we didn't necessarily need a 3,000 PSI cylinder to work the system, but just because of the range of the pressures they were outputting, that was what worked best. And then also the stroke length that we needed, because it's relatively long. So the longer your stroke length, the bigger the cylinder gets. So that's kind of why we chose that cylinder. And if you're talking about actuation, hydraulics was just kind of the way to go because of the durability of that versus an electrical or more mechanically driven system that includes gearing and such.
The other main criteria for that was the cost, and that was definitely cheap.
And if you get a custom hydraulic cylinder, I don't think Ron would be too happy because that would probably be our $5 grand right there.
One more question.
How many of these are you planning on building, and how many trucks? 3. 3, okay.
Okay, I think with one other here, we can fit it in. Yes.
Did you guys end up calculating factor safety for that?
Yeah.
Or I guess what kind of roads it was saying?
Yeah, I can talk a lot about for the FEA analysis. We were we ran it. So Ben put together basically a spreadsheet of the forces that we needed to account for, and we found that the max stress condition was when it was at the basically in the folded up position because were like the sharpest angles there. But then we also did account for fatigue. So with it going up and down, I know Garrett used some Marin factors, right? Just to account for the effects of fatigue and it being used over a long period of time and just running through different cycles. So.
Thank you.